Hello, so today we are doing this problem called minimum path sum, and the problem says we get an n by n grid filled with non-negative numbers, and we want to find a path from the top left to the bottom right that minimizes the sum of all numbers along its path. So we want to minimize the sum of all numbers in that path. It says also you can only move either down or right, so the only directions that we can go to are down and right. So for example, here to go from this one on the top left to the bottom right, the path that minimizes, that does only down or right movement, is going right to 3 and then right to 1 and then down to 1 here and then down to the last one. And this is the minimum sum that we can do to reach the bottom right sum. And so how can we solve this problem, right? Let's try that. Seven is the sum that we are looking for. Okay, so how can we find this? So first thing we can think of, let's just think of brute force solution. But one thing is, if you find the path until some point, you can just minimize the rest up until right and then add them, right? And so that kind of gives you the intuition that you can use recursion here, right? And so what relation can help us? So we know that we can do only two movements, which are down and right? So if you are at position, which means at position ij, we can move only to ij, I plus 1j, which is, this is basically, you can move only down, right? Down to, or right to ij plus 1. So we know the two states that we depend on, right? So now we know the two states that we depend on, and we can keep moving until, keep moving from 0, 0, right, until n minus 1, m minus 1. If we consider that n is the number of rows, n is the number of rows, and m is the number of columns, right? So let's try and write the recursion for this, right? So what is the base case? So for recursion, we need the base case, we need the recurrence, we need the operation that we will do to bring the result of the recurrence together, right? Or the recursion here, this recursion, let's call it something. So the base case here is if I is equal to n minus 1 and j is equal to n minus 1, that means we reached m minus 1, that means we reached the destination, right? So this case, just return the sum, right? There is nowhere else to go. Now what if we at n or we reach j equal to n? So because in this substate we increment just I or j, so maybe in one of them we'll keep incrementing and we reach n, or the other one reach j, but not all of them reached n minus 1 and m minus 1. So this case is not valid, it's outside. So to mark that it's not valid, we should just say, so this is invalid, right? So to mark that it's invalid, we should return something that makes it invalid. But since we are looking for the minimum, so the problem says we want to minimize the sum of the numbers, right? So to get something invalid, which means it won't count no matter what happens, so to do that, and since we are minimizing, let's pass the max number, so that any other number would be the minimum, right? So that this doesn't affect anything in the result, right? And then what is the recursion? So we know it's these two, and so it's just calling the same function. Let's call it helper on I plus 1 j and then on I and j plus 1. But now what is the operation that we want to do? We know that when we are here, we need to add this one, the value, with either the two choices, either going left or going right or going down. And since these two choices, we want to minimize between them, so these are the two choices. Since we want to minimize between them, we can just take the minimum of the two and add it to the grid value. Basically what we are doing is we get to this point and we say to the right one, go get us the minimum path that you can to the right, and once you have that result, I will add my value to you. And we say to the bottom, go you also find the path. So we just tell both to go find the minimum path to the destination, and once they come back with the result, we compare, we take the minimum and we add that to the value here, and we keep doing this recursively, which means that we will guarantee that overall we will find the minimum path sum. And so that would mean here the operation would be the value at ij plus whichever of the two choices is the minimum, which is these two basically. So it's this and this one. And that's pretty much it. What is the result that we should return? It's just we start the recursion at the first position and let the recursion path go and try everything and just find the minimum among all possibilities and return the result. And that's pretty much it. So let's code this up. So to code that, we need to do our base cases. So let's just put them here. This one is invalid case, and we need to start this case here, which is just return that, and we need to define the helper function, of course, so that we can call it. So it finds the minimum path from ij to the bottom right cell, right? So this one here finds the minimum path sum from ij to the bottom right cell, which is just n-1 cell. And we can do the call that we said that we need to call here, which is pretty much this one, and that should do it. So let's run it. Yep, so I need to initialize these n and m values. Okay, sounds about right. Okay, there is a problem with this case. So index out of range, which means that at some point we had so at both, and we are at the position or one of them. Let's just, to avoid that, let's just do this here, even though that shouldn't affect the bug. So it's saying that we have an index out of range at this position, which probably means one of these I or j is too big. Yep, because I'm checking I equal to n or j equal to m. Actually, j is the number of columns, which is m. Okay, sounds right. Submit. Okay, so normal. This is normal to get time limited exception on this. Time limit exceeded because we are using recursion here, and we are computing a lot of cases multiple times. To give you an idea, the complexity, time complexity in this case, it's O of 2 to the power of m plus n. That's the number of overall state that we will visit, and we will recurse on them multiple times. And so with each time we go 2 separate paths because of these 2 choices, and we keep trying all of them, and we do that m plus n times. So it's O of 2 to the power of m plus n. In terms of space complexity, this is O of 1, but we need to do better than this because this is too big. And so the way, this is recursion, and so the way, the usual method that we do this is we do recursion with memoization in a way so that we don't repeat like the calculations, so that, and we save them basically so that we can reduce the time complexity to maybe only m plus n or something similar, only the size of the path, of size of the input, which is m plus n. And so to do that, we just need a map that will save the previously computed solutions. So let's call it memoization, memo here. And whenever we find a solution, we will put it, before returning it, we will save it in this cache thing called memo, and then we return it. And now, before calculating it and going to all its substates, maybe we did calculate it before, so we check if it was calculated before. If it was, we just return what we cached. So at that case, we can just return what we cached here. And that's pretty much it. Okay, that looks right. Submit. Okay, so this solution passes. You can see compared to this one that had the time limit exceeded at the test case 20, or 21. Although the only thing that I changed here is this, using this caching mechanism here, or this recursion with memoization here. Okay, so now when we are able to solve a problem with recursion and then with recursion memoization, it's always a good idea to try to do the direct DP state, a DP solution. Usually people go to do the DP solution first, if they have a lot of experience with this kind of problems. But I think it's beneficial to do this method first until you get used to the intuition of coming up with a DP state that works well. Okay, so let's do the DP solution. So for the DP, we need to know our goal that we need to return. We need to know our state, our base case, the recurrence relation, and potentially the order of iteration if it's not the same as the default one. So what is the goal here? So the goal is to minimize the sum of the numbers along the path, right? So minimum path minimum sum path from 0, 0 to n minus 1, n minus 1, right? So what is the substate of this? So it's just getting to a point before this one, and from that point we can go to this one. So the state can be depending on 2 variables that specify a point, which are just dp of ij, and this one can present just the minimum sum path from 0, 0 to ij. And so that means that, so directly you can see that we deduced the state from the goal right away, so that, because what we want is at the end to be able to return dp of n minus 1, n minus 1, and this is exactly the min sum path from 0, 0 to n minus 1, n minus 1, which is exactly what the goal function says that we should return. And so now what is the base case here for dp, let's say, of 0, 0? So that means minimum sum path from 0, 0 to 0, 0. That's just the value itself, right? So that's just a grid of 0, 0. now what is the recurrence? So the recurrence, we can tell it by the by the substate that we found here. We know that we can move only down or right. Right? And so when we are at a point, let's say ij, since we want, so here we are doing it forward, but in DP it's usually good to use the previous states to find the current state. And so what is the previous state for ij? The only possible use cases is that we came over from the left, so we moved right, or we came over from the top, which means we moved to the bottom, right? So either we came from here or we came from here, right? And so coming from here means it's the I-1j position, and coming from here means it's the ij-1, the previous column, right? So sorry about the noise, by the way. And so this means that I-1j, and this is the position. So the two states that we would have to come from are just these two. And so that means that our DP is going to be a function of I-1j and DP of ij-1, right? And so what is this function? So again, the same logic that I said earlier with this, it's the value at the grid, this one plus whatever value here, the minimum of either coming from here or here, because that's what we want. We want the minimum sum. And so let's just try the two states and pick the minimum. So that means we pick the minimum of these two and we add on to it dp of ij, right? That's pretty much it. So we take dp of ij and we take a function of these two, the minimum of them, and we add the value here. Sorry, this is grid, right? This is the value here, which is grid ij. And so now we have our recurrence relation. Now the order that I set here was that we need to go through the previous cells first. So we need to go through this part first and then come down to the rest, basically. So that would mean just going through, basically means when we are at ij, we need to be sure that we computed I-1j and ij-1 so that this recurrence can work. And so that would mean here we can just go through the range of n and go through the range of, and this way when we are at ij, like let's say 2, 3, we know that we already computed 1, 2, because that's literally the way the for loop works. It's from 0 to 2, and then to 3, and to 4, 0 to 1, to 2, to 3, and 4, and the same thing for j. Okay, so now with this we can write our dp. We'll need to do some special cases for this I-1, because when it's 0 it becomes -1, which is not something we want to use. But overall, this is the template that we should use. And so let's just write that. So we need to have n and m, and that's length of the grid, and that's just the number of rows and the number of columns, right? And so this one is grid 0, and let's just test that grid is not empty. So if it's empty, let's just return 0. And then now we need to create our dp array, which is just gets filled with 0 first for all values, m for the columns, and we do that for n rows. And now we need to start doing, so we know that dp00, which is the base case, should be initialized to this. And now we need to start our loops, and for j is in the range of m. So now we need to handle the case where for I-1 what should happen. So to save against that, I'm just going to start from 1, because I don't want this I-1 to be -1, and then I'm going to handle the 0 case here. So first row, which is basically I equal to 0, I'm going to handle it here. In the first column, which is j equal to 0, I'm going to handle it here, right? So for the first row, let's just go through all the columns and fill the first row. So the first row, you can't, the only way for you to have come from is from a left point, because there is no way to come down from above. There is nothing above. And so for that, the only way is the previous position. And so for those, it's yep. So for that, it's going to be dp of, it's the first row, so 0, and j, and it's going to be equal to, we know that it has to be dp of 0, j minus 1 only, so you need to have come from a previous one, and plus the position at, the element at that position, right? There's only one thing, is also for j, what if j is equal to 0? So we don't want to handle that, because if j is equal to 0, that's dp of 0, 0, and we already handled that here, right? And so we do a similar thing for I, except now it's in the range of 1n, and with the same logic, we already computed 0, 0, so we can skip it. And what we are doing here is for the column, so it's j0, and sorry, I0, yeah. So this one, when you are on the left side, the only way is to have come from above by going down, because there is nothing to the left to come in the right direction from, right? And so for that, that means that we only can come from the top, so it's I minus 1, 0, plus the grid at that position, which is I, 0, right? And now we can do that, we handle the special cases, we can do this. So that means that dp at this position here is equal to that. And now we can return the result that we said here, which is return just this. The other way to do this in Python is to say something like this: dp of minus 1, which will return the last row, and minus 1, which will return the last column. But this should do, so let's just run it. Okay, so seems good. Okay, so that solution passes. Now let's just examine the time complexity for this. So the time complexity here, you can see we are doing O of m plus O of n. So we are doing m here, and then we are doing n after it, and then plus we are doing, after that we are doing n multiplied by m, right? So it's n multiplied by m after it. So this one is the biggest factor, and so this overall is O of nm. In terms of space complexity, we are using this extra dp array, and the rest is just constant variable, so it's constant space, except this dp array, which is of size m by n, so it's the same thing, O of nm space also. So let's see if we can we do better. So for the time complexity, it will hard to do less than m by m, because we need to examine all the rows to find the minimum path, right? There is nothing that says that it's sorted or something that we can take advantage of. So the time complexity, it's hard to move, so I'm not going to think about that, to move it or to find a better one. But for the space complexity, we probably can, because if you look at what we are using every time here for the substate, we don't go to I minus 2 or I minus 3 or I minus 4. We only use, every time we use I minus 1 and j minus 1 in all the states you can see here. Every ij or 0j or I0 depends only on I minus 1 and sometimes j minus 1. And other times, sometimes I minus 1, and sometimes it depends on j minus 1, and sometimes it depends on both. So that tells us right away that we can use keep track only of two columns. Keep track only of of 2 columns, right? But to do that, first I will need to do a slight adjustment, which is make this doesn't change the algorithm at all. Doing j first, it will do the exact same thing. It will just compute it in a different order. But when we get to ij, we'll still have computed both these cases. And so this will just make it easier for me to keep track only of 2 columns. The other way to solve it is to keep track only of 2 rows. That's also valid. But yeah, I'm just going to do it for 2 columns. So we didn't change anything, it still works. And now, so we need to keep track only of 2 columns. So we are going to get rid of this O of n m space and just keep track of 2 columns so that we can end up with O of 2m space. And so to do that, what I'm going to do is, instead of this dp, I'm going to have just a previous column and a current column, and both gets initialized to 0, right? And so that would mean that my previous 0, right, the previous row at 0 is going to be equal to that value instead. And now what I'm going to do is, first, I don't need to do the first row since I'm keeping track only of the columns. I'm going to do the first column, right? And the first column now is going to be saved in prev instead. So that's prev of I. And this one is just the previous value of prev, because the prev would store first the first row, right? And this here, now I'm doing prev of I, right? That's the current, sorry, the current one is going to depend on this value, and the previous one is the one at I minus 1. So basically, the previous column is all j minus 1 values, right? And the current column, that's all j values. So it can have I minus 1, I, and the values after that. But we will need only these 2. And here it's all j minus 1, so it's the things like basically I j minus 1 gets replaced here. And for this one, it's the I value, so I minus 1 j's or ij, those are the current values, right? Because that's the current column, because the current column is j, the previous column is j minus 1. So this one here, it's I minus 1, but it's j, so it's the current column. So that's just current. But so I messed up something here. This is the first column, right? And so the first column, the value is actually at 0 I. Sorry, I made a mistake. Here it's I0. I should keep it that way. Yep. Because this is the column, the first column, right? And so here, with that, I'm having the grid, and this here, it's this is the current. So this one is the previous, right? So this one is the previous. So it's previous I. That's the previous column. And this one here is the previous, so I minus 1j, this is the current value. Okay, let me just backtrack a little bit. I think this maybe confuse people. I think keeping track of columns will be confusing a little bit. Let's just keep it as the rows and change it to keep track of 2 rows instead. So I'm just going to keep track instead of 2 rows. And so that would mean I will have this, that's a row, and both of them are constitute 2 rows. So prev, previous row, and current is going to be current row, right? And so that would mean I need to keep track of this one, because this one fills the first row, but I don't need to do this one anymore. And now this one is going to be the previous value, right? So previous for j is going to be previous of j minus 1 plus grid of 0g. So we're not changing that, and let's just keep the order that we had before, which is I to n and j to m, right? And now the previous row, this one is anything that is dp, that was dp for I minus 1 something, right? And the current row is anything that has dpi, right? So that means that dpi here, this is the current value, right, at j, right? And this one stays the same, and this one I minus 1 is the previous row, so that's previous. And this one is the current row, so that's current. And that's pretty much it. So the only change is that when we completely fill this current row, prev needs to become that previous current, that current for the next iteration. So for each iteration, let's say we did the first row and then we did the second row. For the third row, the previous value needs to be the second row that we just computed, right? So that's what we are doing here. And at the end, we need to return the last one, which would be current of n minus 1, or we can just do current minus 1 to get the last value in current, because that's the last one that got filled in the iteration. And that's pretty much it. There's only one thing here, is that before we were filling the columns in a separate loop, so I should fill them here still. So what is the column for the current here? So current value at 0 should be equal to the grid value at I 0, right? So this fills basically the column values. For every time we are examining a row, we fill up the start cell with its value. And so that's prev of I 0, but plus whatever was in the previous row. Right, because in order to get here, we can also have used the previous row plus the value here, right? It's not just the value itself, it's the value plus whatever we did to go from the start 0, 0 to that cell, right? So that's why we are doing here previous row plus the cell value. So this is prev, and that's pretty much it. So let's run this. Yep, so this is prev. So there is a small additional value here. Yep, so I should go from 1 to n. That's the length of the rows, right? Sorry about that. Okay, so that looks good. Okay, so now we optimize the space. So time complexity, we didn't change it, but the space complexity now is just, we are using just 2 rows. So it's just the 2 multiplied by m, right? Size of 2 columns, size of the size of columns 2 times for each row, right? So this is O of m roughly. So can we do better than that? Actually, one thing we can do is, instead of using 2 rows, we can just use 1 row. It will still be the same complexity, right? But if we have really long grids, that can make a difference, right? And so to do that, we notice that here for this prev g, the value is actually just the current g before changing it, because literally what we are doing is assigning prev to the current row, so that next time we can use it here. But next time, before replacing the value of current j, the value that it is in that array cell is exactly the previous j, because that's literally what we are doing. So what we can do is just get rid of this and just make this the current, and now just fill this with current values. And no need for this, we can just add to it because the value is already at current. And now the previous is just what is in current j before updating it, and we no longer need this since it's already in it. And that's pretty much it, right? So let's run this. Okay, so that does seem to work. Okay, so now it passes, and this one is the complexity is right away over, right? Time complexity is still the same though. There is another way to do this without like using any extra space, basically of one constant space, and that just by changing the values in the grid itself. So overriding the values in the grid to keep track of the sum, because of the order we are traversing, we don't ever visit another one that we already visited. And so if we can just store the values in the cells themselves, and that way the last value is just a grid of n-1, n-1. You can try that. I'm not going to do it here, but it's straightforward to do. Yeah, so that's it for this solution. Thanks for watching, and see you next time. Bye.